Hello, and welcome to a short video on using high-resolution instruments in commerce. This is directly related to NCWM items scale 20.10 and 20.11. I argued against paragraph S1222 when it was added in 2017. What I did then, and I will do now, is say that the issue of high resolution is a global issue, and there are many instances of instruments with different resolution in commerce, and we have to take that into account and look at it as a global and not just a scales code issue. If we understand resolution, we recognize that the scale division D is not necessarily tied to the tolerance of the instrument as expressed in E, the verification scale division. Since they're independent, we can have differing relationships between D and the tolerance. The most common relationship is what we call normal resolution, where E is about the same magnitude as D. And I say about the same magnitude because the tolerances may be expressed in a different unit of measure that may not produce exact equivalence. Instruments of normal resolution typically use normal rounding. And of course, we can look at examples throughout the codes, and most of the devices in most of the codes are normal resolution, normal rounding. There are also low resolution instruments where the scale division D is significantly larger than E. What we find is these instruments can either be rounded up or rounded down in their rounding. They're not normal rounding. So, for example, we have residential water meters that are rounded down. We have taximeters and weight classifiers that are rounded up. That brings us to the high-resolution instruments, the ones that are subject of this presentation, and here we see that the scale division D is an order of magnitude smaller than E. Instruments of this type typically use normal rounding, and I'd like to point to a couple of examples. The first example are the class 1 and 2 scales with a differentiated D. For example, where E equals 10D. The class 2 tolerance at 20,000 E for one of these instruments can be expressed as 20 scale divisions, 2E, 20D. But there are other high-resolution instruments that we need to consider. The next is the motor fuel dispenser, and there's a reason that I used it in some of the other videos. What we see is the tolerance at 5 gallons on one of these instruments is 26 scale divisions. Now, the manufacturer could have used 0.01 gallon divisions, which would have made it a normal resolution instrument, and the 5 gallon tolerance would have been 2.6 divisions. The third high resolution instrument is the class 3L scale. And this is somewhat difficult for people to grasp because the tolerance at 10,000 E for class 3L is 20 scale divisions. That's a lot of scale divisions of tolerance. Class 3L is an anomaly in the scales code. Anomaly because the accuracy is 0.2% throughout the class range. If you'll remember, in my second video, I showed that as you get more divisions within a class, the accuracy goes up. But in this case, it's not true. So whether you have n equals 2,000 or n equals 10,000, you have the same accuracy. But the class 3 part of 3L is really important because essentially this is a class 3 instrument where E equals 5D or E equals 10D and N is less than or equal to 1,000. Perfect example, the prototypical class 3 instrument people talk about is 20,000 pound by 20 pound. Now that is accuracy equivalent to a class 3 scale that's 200,000 pounds by 200 pounds, or N equals 1,000. People might ask, don't you mean 50 pound? Well, no, because at 50 pound, that would be 4,000 divisions in class 3, and the tolerance is 3 divisions, which is 150 pounds of tolerance at 200,000. That's not equivalent to the 400-pound tolerance in class 3L. So we see that the class 3 tolerances up to 100,000 pounds, 500E is 1E or 200 pounds, from 100,000 to 200,000, 2E, 400 pounds. Better way to look at this, though, is a little graph. The blue line represents class 3L and all the steps of class 3L. The dotted red line represents the class 3 with 200-pound scale divisions. What's really important is, for many reasons, the manufacturer is not allowed to invade the pink space under the red steps. The envelope of performance, whether it's 200,000 by 200 or 200,000 by 20 class 3L, is essentially the same. So why use high resolution instruments? The first reason is actually the reason of why they came into being for class 1 and 2, and that is it became difficult to test these instruments because as you get down to 10 milligrams and 1 milligram scale divisions, you do not have weights that you can use to determine the errors. And so the scale manufacturer actually expands the resolution so that you can see the errors. So with class 1 and 2 scales with a differentiated digit reading to 0.2E or 0.1E, you satisfy the requirement to reduce the rounding error when determining the scale errors. What's really interesting is that this should also apply to class 3L. You see, when class 3L gets at least 5,000 scale divisions, you already meet the 0.2E requirement relative to class 3. So basically what you see is that NTEP goes out and uses 2-pound error weights to measure errors of 200 and 400 pounds. A second reason why we use high-resolution instruments is to reduce pricing increments in trade. The fuel dispenser is the perfect example. Manufacturers chose to use 0.001 gallon divisions because they wanted to keep price increments to 1 cent. They wanted to get whole dollar amounts at all unit prices. The same is true of Class 2 and Class 3L. When you have a $30 a gram item, then an E of 0.1 gram means every scale division is $3. By going to E equals 10D, you reduce that to 30 cents per division. The same is true of Class 3L. If we had to measure stuff in 200-pound scale divisions, even cheap stuff like trash would be $20 for every scale division. And the high-resolution instrument reduces that. There's a third reason to use high-resolution instruments, and that's because you can measure smaller quantities with the same instrument. Basically, instruments have increased relative error at small quantities due to the rounding error to the scale division D. When you make D smaller, you can measure smaller on the instrument. And we limit the use of the instrument at low quantities. For example, liquid measuring devices require, according to the general code, 100 D. So for the typical motor fuel dispenser, that's 1/10 of a gallon. And weighing instruments, we use table 8. And you will notice that we have made some proposed changes to that in the block 2 items. A couple of burning questions remain. First, why do we differentiate D for class 1 and 2? Originally, it was to show that the instrument was resolving to a finer D. It's important to see that the D was not differentiated because it was inaccurate or invalid. I think what I've shown in the previous 2 videos is that it definitely is accurate and it definitely is valid. Now, I point out that there are other high-resolution instruments like fuel dispensers and Class 3L. They don't have to differentiate the least significant digit, and they're permitted in commerce and in direct sale. The other thing is I don't believe people are confused because of the differentiated digit. They're not confused by gasoline prices where the 10th cent is differentiated. I believe as D is differentiated to assure the regulatory official does not mistakenly assume E equals D for these devices, and I find no other reason. The other burning question is, should we ban high-resolution instruments? Of course, they were banned in S1222 that we're talking about repealing or amending. But I point out that other high-resolution instruments are permitted in the Handbook 44 codes without restriction. And there are also low-resolution weight classifiers and taximeters allowed in direct sale. Now, do the buyers or sellers really care? Provided the instrument meets the needs of the application. And I ask, where's the harm in increasing resolution to reduce pricing increments and allow instruments to measure smaller quantities? And then I close by showing that there is no reduction in accuracy. In fact, I think we can show that relative accuracy is increased, particularly at light loads. I've done a model here, and we have to stop for a second thinking about an individual instrument and think about the population. This model is talking about a whole bunch of transactions on a whole bunch of different instruments. There are 3 sources of error. In every measurement, you have a 0 setting error. If you don't start at exactly 0, you affect all of the measurements. Then you have the rounding error to a half a D, and then you have the linearity error. That is the deviation of the instrument from its true value. In verification tests, we go to great lengths to reduce that rounding error. But in transactions, that rounding error is always included. And smaller d produces smaller rounding error and smaller 0 errors, yielding more accurate transactions. And what it means is, in reality, with a equals 10D instrument, you'll see that the chances of failing that instrument at the first tolerance step of 5000 E is actually quite small. So essentially, I'm coming down in strong support of allowing high-resolution instruments in commerce, and particularly for jewelers and cannabis trade. I thank you very much for listening.